One important aspect of a function is its associated domain, which indicates the set on which the function is defined. If we think of a function as a machine which takes in an input x and spits out an output f of x, then the domain consists of all those x's that we can plug in. That is, the domain is the set of x for which f of x makes sense. This is a reasonable thing to consider because not all algebraic expressions involving x make sense for each input x. For example, the expression 1 over x, or the reciprocal of x, defines a function of the variable x, but it does not make sense for x equals 0 because we can't divide by 0. This means that the number 0 is excluded from the domain of this function. In fact, 0 is the only number excluded from the domain, so the domain consists of all the points that are not equal to 0. We can visualize this set geometrically on the number line. It's common to draw an open circle around the point 0 because 0 is not included. In this way, we see that the domain consists of two different intervals, one to the left of 0 and one to the right of 0. Another way of writing the domain, then, is in interval notation, as the union of the set from minus infinity to 0 with the set from 0 to infinity. It's common to use parentheses when the endpoint is excluded from the interval, which we have done in each interval around 0. As another example, consider this function involving the square root. The root function is defined if and only if the expression inside the root is greater than or equal to 0. So the domain consists of those points x such that 1 minus x squared is greater than or equal to 0. You could just note that this is the only condition on the domain and call it a day, but it's helpful to realize what set of points this actually is. To solve an inequality involving a polynomial like this one common method is to first plot the roots of the polynomial, which, in this case, are minus 1 and 1. These roots divide the number line into intervals, and the polynomial only takes one sign on each interval. To test the sign of the polynomial for the given interval, it's common just to plug in a specific value of x in that interval and check whether the sign of the polynomial is positive or negative at that point. For example, at the point x equals 0, the polynomial takes the value 1, which is positive. So this means that the polynomial is positive on the middle interval, from minus 1 to 1. In a similar fashion, it's not too difficult to check that the polynomial is negative on the other two intervals. Another way of seeing this is to just realize that the expression 1 minus x squared certainly grows negative for x very, very large. What this all means is that the domain of this function consists precisely of the middle interval only, which, in terms of interval notation, is just the set from minus 1 to 1. The square brackets in this case indicate that the endpoints are to be included in the interval. That is, 1 and minus 1 are both valid points that we could plug in. Some algebraic expressions are even more complicated, involving multiple pieces. For example, this function is the sum of the previous two functions that we considered. In such a situation, the domain consists of the intersection of the domains of each of the pieces. In other words, an input is valid if and only if it works for both pieces simultaneously. The valid inputs for the first summand were found to be all x that are non-zero, and the valid inputs for the second summand were found to be all x between minus 1 and 1. It follows, therefore, that the domain of the sum of these expressions is equal to the non-zero points between minus 1 and 1. In terms of interval notation, this is the union of the interval from minus 1 to 0 with the interval from 0 to 1. To reiterate, closed brackets are used around endpoints that are included, whereas open parentheses are used around endpoints that are not included. In particular, 0 is excluded from the domain, whereas both minus 1 and 1 are valid points in the domain.